This is a Queen Mary's College video on the reactions of benzene. So if you can make sure you've got the knowledge pack Molecules by Design open at section 5.6. The first reaction is the reaction between bromine and benzene. An electrophile is produced. It's the Br plus ion. The Br plus ion has an incomplete outer shell, as you can see from the diagram, just 6 electrons in the outer shell. That makes it an electrophile and strongly attracted to regions of high electron density found in the benzene molecule. An iron catalyst is required. The iron reacts with bromine, producing iron 3 bromide. And the iron 3 bromide promotes the production of a dipole on the bromine to bromine molecule. You can see that the lone pair of electrons on the bromine molecule is used to fill an empty orbital of the iron atom, and this generates the bromine electrophile. This is the mechanism for the reaction, which in fact you don't need for Salter's chemistry exams. You remember the benzene ring has 6 delocalized electrons, and 2 out of these 6 electrons, delocalized electrons, are used to form a new covalent bond between the carbon and the bromine. So you can see the electrophile has added on to the ring, and as a consequence of those electrons being used to form the new bond between the carbon and the bromine, we've got an incomplete benzene ring. To re-establish the benzene ring, the 2 electrons of the carbon to hydrogen bond are used to produce the stable product, bromobenzene, and you can see the hydrogen replaced is produced as hydrogen ions. So here's the overall equation for bromination. You can see the product is bromobenzene and the other product hydrogen bromide. Chlorination is very similar. One difference is the catalyst. We've got aluminium chloride, which supports the production of the chlorine electrophile, Cl+. Aluminium chloride does react with water, so anhydrous conditions are required. And the product is chlorobenzene. Hydrogen chloride as the co-product. Let's take a look at the nitration of benzene. This requires a nitrating mixture, which is a mixture of concentrated nitric acid together with concentrated sulfuric acid. So these 2 acids produce the electrophile in bold. This is the nitronium ion, NO2 with a plus charge. Keeping the temperature below 55 degrees means that multiple substitutions are avoided. Let's take a look at the equation for the reaction. You can see the NO2 group has substituted the benzene ring, so that gives us nitrobenzene, and the co-product is water. Let's take a look at one of 2 Friedel-Krauss reactions. The first one is alkylation. The simplest version of this is methylation. Simply produces the methyl electrophile, that's CH3 with a positive charge, and that's produced from chloromethane. Catalyst aluminium chloride, that's used to polarize chloromethane to enhance the production of the dipole. The lone pair on the chlorine is used to complete the outer shell of the aluminium chloride molecule, and this promotes the production of the electrophile CH3 with a positive charge. And you can see there the methyl group CH3, the positive charge, does have an incomplete outer shell, so it fits the definition of an electrophile. So the CH3 group with a positive charge substitutes the benzene ring, giving us methyl benzene, and the general representation for alkylation using the R group. You can see the R group substitutes the ring, and the hydrogen and the chlorine come together as the co-product, hydrogen chloride. So here's the equation again. You can see the product is methyl benzene, the methyl group coming from the 1 carbon halogen chloromethane. Catalyst aluminium chloride reacts with water, so anhydrous conditions have to be used. So the second of the two Friedel-Crafts reactions is acylation. If we use ethanol chloride, the 2 carbon acyl chloride, we've got ethanolation. So the acyl group is the RCO+, and if we use ethanol chloride, that gives us the ethanol electrophile CH3CO with a positive charge. The same catalyst as before, used to enhance the production of the dipole on the carbon to chlorine bond. The lone pair on the chlorine is used to complete the outer shell of the aluminium atom in the aluminium chloride, and that enhances the production of the electrophile. The acyl group, the 2 carbon acyl group, CH3CO with a positive charge. So here's the reaction again, showing the ethanol group substituted onto the benzene ring. So the chlorine of the ethanol chloride teams up with the hydrogen that's been substituted, giving us HCl fumes. And here's the general representation. So the overall reaction, you can see the 2 carbon acyl group, the ethanol group, has substituted the hydrogen, and we have a product which is in fact a ketone, and conditions as shown there. This is the last of the benzene reactions, sulfonation. Uses concentrated sulfuric acid, and boiling under reflux produces the electrophile SO3 sulfur trioxide. The product is benzene sulfonic acid. We've got the sulfonic acid group SO3H substituting the benzene ring. Here's some extra detail about the mechanism. Like I said, you don't need to recall the electrophilic substitution mechanism. So we've got the stable product there, the benzene ring re-established. The hydrogen has been lost as hydrogen ions, teams up with the oxygen with the negative charge, lone pair used to form a new covalent bond there, giving us the product benzene sulfonic acid.